Hello, welcome to this Vib Tip session. Today we are going to talk about other vibration test feedback sensors different from accelerometers, like laser vibrometers and wireless accelerometers. One possible use of a laser vibrometer is vibration testing control. There are some applications where an accelerometer is not the most suitable solution for vibration testing feedback control, and a non-contact sensor, as a laser vibrometer, can be the best choice. Laser vibrometers are based on the Doppler effect. Light reflected from a moving object is subject to a change in frequency proportional to the object's velocity. The laser sends a wave to the vibrating DUT that, since the DUT is approaching or receding, its reflected and successive wave crests reach the detector in smaller or larger time intervals than they had been emitted. This shift in frequency is known as Doppler effect. The measured frequency shift of laser with defined wavelength lambda c is proportional to the velocity, and we can use this velocity as feedback signal of our vibration testing control loop. Velocity of the surface is measured collinear to the beam direction with up to an amazing high sampling rate of 160 million samples per second, and consequently an extremely high resolution. An acoustic example is the apparent change in tone pitch detected by a pedestrian when a train is crossing a station. We can consider three applications where the use of a classical accelerometer is not the best option. When the DUT is light and since its resonance frequency and dynamic behavior depends on the mass, adding the weight of an accelerometer can become significant. An example can be vibration testing of a turbine blade. Another application is when the DUT is smaller than the sensor, for example when measuring acceleration in integrated circuits. Sensors must be able to operate under a test range of environmental conditions, including extreme levels. Some DUTs produce high temperatures while in use, as an exhaust pipe, and a non-contact sensor may be a better measurement option. Wireless accelerometers could be considered as a convenient technical solution to remove cabling between the sensor and the controller. However, we'll see that they still need some further development to really become the accurate and reliable sensor that we need in vibration testing. A wireless triaxial accelerometer looks similar to the image. It's bigger and heavier than a typical piezoelectric accelerometer, and this can be really challenging for many shaker table applications. However, we can just fix it to the measurement location without any cable, and it will transmit to a receiver that we would connect to our controller's input channels. Although this configuration looks really nice, it has several drawbacks. The first major hurdle is that most of the wireless sensors only transmit point data. They don't transmit time waveform data continuously. There may be a few that transmit a block or frame of a time waveform data, but that's about it. The second difficulty with wireless sensors for use with shaker tables is the battery life. Even if wireless sensors could transmit continuous time waveform data, they could burn through their battery life quickly. The third issue is the performance. Since most of these accelerometers are MEMS based, the frequency response and the noise level show lower performances than piezoelectric sensors. Also, the sensitivity of some of the brands is not well situated for vibration control and monitoring on shaker tables. The resonance frequency of a piezoelectric accelerometer can be pretty high compared with the testing frequency, and its effect only starts to be appreciable around 20%. In the image, we can see that for a typical test frequency range of 10 to 2000 Hz, the sensitivity variation of piezoelectric accelerometers can be within ±3% or less, while MEMS show a much lower resonance frequency, and the variation of the output level can be within ±3 but dBs, so significantly higher than piezoelectric. This particular drawback could be solved with this alternative possible configuration, where we can use piezoelectric accelerometers with good frequency response function connected to a hardware called gateway that transmits the signal to the receiver. Vibration and shock data gathering is, however, a suitable application for this type of sensor, since data is usually taken in time blocks, either in fixed time intervals or when recording is activated by a threshold level. Battery life is preserved, and high accuracy is not so critical, since we will post-process that information to generate a statistically calculated PSD that somehow averages the acquired data. Summarizing, for those cases where the use of a typical accelerometer is challenging, there are other sensors options that can solve the problem. Laser vibrometers are a fantastic tool for this purpose, although the current relatively high cost limits its widespread use. Wireless accelerometers are a future option for vibration control, but still need some further development. Want to learn more? Invest in education and sign up for our training courses. Thanks for attending, and let's meet in the next Vib Tip session.